Now that we have a good basic understanding of WebKit internals, let's improve on our knowledge by looking at the actual exploit from Linus. We already saw it executing perfectly on Safari in an earlier video, so this time let's just focus on the implementation. So the index.html simply has a link to pwn.html, and there we see a few JavaScript files being included: ready, logging, utils, int64, and finally pwn.js. We will eventually learn about all their purposes, but I would say let's start with the pwn.js. This is quite a long script that has over 530 lines of code, and it does all the fancy stuff to get to arbitrary code execution. So it will take some work to understand the different steps. But let's start at the top and look for the actual vulnerability that is being exploited. I want to start by looking at the first two functions, addrof internal and addrof, and I copy them into a new script, test.js. The comment here says address of primitive, and what that means is super important, but I will get to that another time. For now, just accept that this function addressOf is supposed to return the actual memory address of a JavaScript object. So we should be able to call addressOf with an object, and that should give us the address in memory of it. We can quickly test it. Instead of running JSC as a JavaScript interpreter, we can also pass the test.js file to it. Also, if you run into this error, symbol not found, then in case of Mac, you need to set the dynamic loader framework path to the debug build directory, and then it works. Here we get the output. A super weird float number. It looks weird, but let's quickly decode it with Python. We can use struct again. First we pack it back into a raw byte string, and then instead of decoding it as a double, we decode it as a 64-bit integer, and then we display it as hex. There we go. That is the real address. We could even print the scribe of this object before we call addressOf, which is this debug function inside of JSC to let us get some memory info, and when we then execute that, we see that the address is correct. So these two functions somehow were able to leak the memory address of this object. But how? The addressOf function calls the addressOf internal function multiple times until the result of it is not an object and also not the double 13.37. Apparently Linus had to wrap the addressOf internal because it sometimes fails. Don't know why, but this works. Well, okay then. Anyway, this means the magic should happen in addressOf internal. It starts by creating an array with a single double, 13.37. If we peek ahead at the return, we see that it calls addressGetter, which should return the first element of the array. And so now the check in the wrapper makes sense. If it's still 13.37, then we try again. So somehow this first element of array should change into the address of the object. Anyway, we also have a regular expression object, reg, with the option y. The y option stands for sticky, which is a special option for how the regex should behave. Now, if you remember the bug description for this WebKit exploit, you know that the bug happens because of an optimization error in the way regex matching is handled. So this regex is obviously crucial. Next, we see a function getArray, which just returns the array. And actually, this seems like redundant code for me. Not sure why Linus assigns the array to array like that, because the array never changes, so I removed that. In the same way, this comparison in here seems weird too. It takes the val and checks if it's null, but we always pass in something for val, so it should always be false. And actually, from just testing it, I noticed that it's not even needed at all. Can be empty. Maybe just left over from during testing and development. Anyway. This addressGetter function is actually called in this for loop below 100,000 times. And the comment says force optimization. And from my video about the JIT compiler, we know that this way we can force that this function is JIT optimized. The for loop in this function here is actually not doing anything, but serves a special purpose. From a commented exploit by Saelo about a similar issue, and an exploit Linus got a lot of inspiration from, Saelo does the same and has this comment, some code to avoid inlining. The JIT compiler could also inline some functions for optimization, but if they are more complex like that, it can be avoided, I guess. However, I also removed this loop as a test, and it looks like this exploit still works. So that's probably just one of these patterns that you do just to be 100% sure, but in this case also not needed. So this leaves us with this. It simply calls the mesh function on the regular expression and then returns the first element of the array. The first thing I was really confused about was this weird symbol.match thing. I have read a lot of JavaScript in my life, but I've never seen that construct. But it turns out that this is actually just a standard thing for regular expressions. The Mozilla developer docs writes, the symbol match, well-known symbol, well-known, specifies the matching of a regular expression against a string. This function is called by the string prototype match method. Okay, so this is just fancy people JavaScript for calling match, and I figured that you can also just write it the typical way of taking some string ABC and then calling match with the regular expression reg. So what this means is this function simply calls a regular expression match and returns the first element of the array, and that code is JITted. So this is now compiled to machine code, and because we know the JIT compiler optimizes, we also can understand that because the JIT knows that the array is a double array, that it just returns a double, without checking if this is still really a double array. However, this should not be a problem, because as soon as something would have side effects inside of the JITted code, it would be discarded, right? Well, let's continue. Next we create a new JavaScript object, regExLastIndex, and assign a function to the toString method. And here we then set the first element of the array to an object. Now this of course changes the array once executed. Remember the JavaScript core internals video when we played around with adding different types to an array? So when we use our debug environment again to check the type of the array with the 13.37 double, we see that it's an array with doubles. And in memory we can also find that element here. This is the 13.37. Now if we modify the first element of the array and set it to an object and describe the array again, it changes to an array with contiguous. And if we look at the butterfly address now, we see that now the first element is a pointer to that object, somewhere else in memory. I guess you can slowly see where this is going. Now back to the exploit code. We then assign this object with our toString function to the regex property lastIndex. So at this point we just prepare this function that will set the first element of the array to our val, but it's not executed yet. However, if lastIndex would be accessed, maybe this toString is executed. The lastIndex is a read-write integer property of regular expression instances that specifies the index at which to start the next match. So internally, regex might read from this property to know where to start the next match. And well, JavaScript or weakly typed programming languages are fun. So instead of it being an integer now, it's now this object which has a toString method that will do this array assignment. And now we trigger the bug. Now we just do it. We call addressGetter again, and we know that addressGetter is now JITted optimized code. This machine code will now execute a regular expression match with our regular expression, but something is different. Before, when we were JITting that function, we hadn't modified the lastIndex property yet, but now we have. And remember the Y for sticky in our regex? The sticky property reflects whether or not the search is sticky, which means it searches in strings only from the index indicated by the lastIndex property of this regular expression. So the internal regex code now has to look at the index property, but it notices, oh, that's not a number, that's an object. So let's try to convert this somehow and let's execute toString on it to see if we can get anything that looks like a number, and this now triggered this assignment. The array now got updated and the first element set to our object val, and the bug happened. The JavaScript engine does not bail out of the JITted code. It thinks that the array didn't change and returns the first element of the array as if it were a double. But in fact it's a pointer to an object now. And when we return that and print it, we leak the address of the object. Amazing, right? But let's go one layer deeper into the rabbit hole and have a closer look. From the WebKit blog about the debugging stuff, we learned about different environment variables for debugging, and I decided to check out JSC report DFG compile times true. So this should tell us when something is optimized by DFG or FTL. I also add a print to the wrapper loop that keeps attempting to trigger the bug to see how many attempts it takes. And this is when I noticed that in the first attempt that failed, the addressGetter function is optimized twice, once with DFG and then FTL. But in the next iteration, when it worked, it only did DFG. So I was thinking, maybe we ran that loop too much. And actually going down from 100,000 to 10,000 iterations to hopefully stay only at the DFG JIT level, yes, the bug works right away. So we can actually remove the wrapper that retries and just call this directly, even more clean now. The next thing I did was using the JSC dump source at DFG time. So that shows us all the JavaScript sources that will be optimized. And this is super interesting because it really shows us the issue. So here's the source of our address getter function that we optimize, and that code uses string match. And so below we also see that it inlined and thus also optimized this regex match JavaScript code. Now that maybe sounds weird, but it turns out that the JavaScript core implements a lot of normal built-in functions, not in C++, but also in JavaScript. So here in built-ins string prototype.js, we find the source code of the match function. So this is also being optimized. And when you look at the code, you can also see it simply calls out the match symbol function of the regex, basically what Linus had directly in his exploit. And then we can also see that it inlined and optimized the symbol.match code, which can be found in the regexp prototype.js file. Here it is just called match. And look at this. The code here has a function call, has observable side effects for regex match. And if it has side effects, it will call match slow. But if it determines that it doesn't have side effects, it calls regexp match fast. And so in our exploit case, it looks at a few different things and decides that it has no side effects and takes the fast path. Now looking at the patch for this vulnerability, we can see that they added a check to this has observable side effects function. And this new check checks if the last index property of the regex is a number. And in our exploit case, we set it to an object with this toString function, which means in the case of the patch here, it would fail this test and would, instead of the fast path, take the slow path. That's how they fixed it. Now how and where exactly the slow path does not result in the same issue, I don't really know. As you know, I'm just learning this too, and the code is not easy to read and reason about. However, I do know that the fast path, so regexp match fast, is in fact a, so to say, instruction. It's its own opcode, at least inside of the DFG, the data flow graph. In the DFG abstract interpreter, for example, we see a big switch case that takes a node from the graph and checks its opcode. And here we have the regexp match fast opcode as well. And now compare it to the one above, the regex test. Here you can see the function clobber world, which means if this operation is used, the JIT can't trust the structures of objects anymore. And the comment here actually says why. Even if we've proven to know input types as regexp object and string, accessing last index is effectful if it's a global regex. So I guess here they thought about that accessing last index could execute arbitrary JavaScript leading to side effects and thus destroy any assumptions. However, it was forgotten for regex match. Really, really cool, right?